Alright, this video is designed to help you with what are called geometric series. And basically a geometric series is just all the terms of a geometric sequence added up. So the sequence over here at the right, or the summation over here at the right, the series, is really just the summation of this sequence right here, 7 times 0.75 to the I. And again, if it looks like an exponential, it's a number raised to a variable. That's also what we call in sort of sequence language a geometric sequence. So again, if you need to learn about geometric sequences first, please pause the video and you can always go look up a geometric sequence video. But this video is going to assume that you do know how to work with a geometric sequence. Now, we have an old shortcut for sequences like the one, or the summation like the one over here at the left. Notice 7i minus 3 is not I to a power, right? It's not 7 raised to the I. This was an arithmetic summation. So it's kind of nice because we had a shortcut that said, for arithmetics, if I take the first term plus the last term, so 382 was just taking 55, plugging it in, and then I take 55 terms divided by 2, I kind of had a nice little shortcut formula in order to find my answer. I didn't have to actually add up 55 terms. Now, at the right, notice we only have 3 terms. So that is very doable. I could plug in 1 and 2 and 3 and get my 3 terms. And they're not that hard to find. Again, 7 times 0.75, 7 times 0.75 squared. Type them into the calculator. And if I add them up very quickly, again, try not to round too much, but if I add them up and round to 3 places at the very end, I should end up with a nice, clean answer. However, terms 1 to 100, I really don't want to add up those 100 terms. Or what I've had many a student ask me, "Excuse me, Mr. Picard," very nicely, "but may we have the shortcut now?" And of course I replied, "Yes, and thanks for asking," like I said, oh so nicely. Let's go get ourselves that shortcut. A geometric series can be sort of found by taking the first term of the series, or the summation, times 1 minus the common ratio. Remember, a geometric sequence has a common ratio. That's just the number that's being raised to the power. So right now, right below here, 1.4 is to the power of I. 1.4 is our R value. And then R to the n on top, and just 1 minus R on the bottom. Notice that entire fraction multiplied by the first term. So if we take that first 100 terms of our sequence here, we would say, okay, well, we're going to plug in 1. I need to find a sub 1. So 12 times 1.4 to the first goes in front. Then I'm going to take 1 minus R, or 1.4. Remember, right now, this, right, let me grab my pen here, this is our R value, right, that 1.4. N, again, was our number of terms, so that was 100 up there. And then I've got 1 minus 1.4 on the bottom. Type very carefully into your calculator. Again, I would recommend parentheses around the top of our fraction, as well as around the bottom. Let's make sure it does those subtractions before it does the division. But then, very quick and simple, we should be able to find our answer. And realize that, again, geometric sequences get very large very quickly. For a series, we're adding up 100 terms of that sequence. So even if we're multiplying by 1.4, things don't seem like they'll grow that fast. They are going to. As soon as we take that to the 100th term, that's already going to be a very, very, very large number. So don't be surprised if you get a little bit of scientific notation today. Now, the sequence, or the summation at the right, the series here, the summation of terms 1 to infinity of a geometric sequence, this is what's called an infinite geometric series. And unfortunately, we can't plug infinity in for n in our previous formula. R to the infinity is just not something we can find. But luckily, if we sort of imagine, as long as R is less than 1, so notice over here we're at 0.1, each term of our sequence is going to get smaller and smaller and smaller. And if we can get those terms infinitely smaller, right, 1/10 every single time compared to its previous step, if we go infinitely smaller, they're just going to essentially become 0. And so this R to the n right here would essentially become 0. And we can get a brand new formula. A sub 1 times 1 would be on top over 1 minus R. Again, this also assumes, though, that R, or the absolute value of R, is less than 1, which for us it is right now. So then we can take our formula and we'll just plug things in. Again, plug in 1. 3 times 0.1 would be 0.3. So that's my a sub 1 out in front here. Then that times 1 would be give me what's up on top. 1 minus 0.1 would be 0.9. And 0.3 over 0.9 would cleanly be 1/3. So again, we have a way to find both finite, if we have a definite number of terms, or infinite geometric series. So let's take a look at a couple of those very quickly here. Again, if it's going to be an infinite summation, so 1 to infinity, as long as r is less than 1, I can just plug that information in my formula. Plug in 1 for n. 10 times 0.3 would be 3. 1 minus r on the bottom, which would be 0.7. And 3 divided by 0.7 is 4.286. Again, another infinite summation. Note this time, though, r would be 7. R is always the number raised to the exponent. And the problem is, that means every term is going to get bigger and bigger and bigger. So there is no sum. We say that it never converges. It's never going to get small enough that we're adding on 0 at the end, or something essentially close to 0. It's never going to stop growing. So therefore, we can't find the sum. It would just go to infinity. Right? The best possible answer you could give is either no sum, or we would just say it's going to infinity. It's just getting bigger and bigger and bigger. That r value needs to be less than 1, or the absolute value of. Because notice over here we've got a -2. So they can be a negative number inside the parentheses. Which again would be a problem for an infinite series, except note the directions on this one. It says only find the 8th partial sum, which means instead of going to infinity, we're only going to go to 8 terms. So if r is -2, again 1 minus r on the bottom, 1 minus -2 would have been 3. Plug in 1 over here. 1 minus 1 is 0. -2 to the 0 is 1. And 6 times 1 is 6. So notice here's a sub 1. I got my first term, 1 minus r to the 8th. All over 1 minus r, or essentially 3 right now. Type carefully into your calculator, and we end up getting -510. So we can find that one because it's an 8th partial sum, just the first 8 terms. Now, down here at the bottom, notice they gave us this series. However, they didn't actually put it in series notation. Or notice it's asking us, find the sigma notation, then evaluate. So what we should do first is start to figure out, okay, is this geometric to begin with? If it's not geometric, we can't use all the shortcut formulas we've been using. So again, a quick way to find a geometric is to figure out, is each term divided by its previous term equal to the same number? Do we have a common ratio? 96 divided by 24 is 4. And if I double check, 384 divided by 96 is also 4. So since I'm getting a common ratio, every term divided by its previous term is giving me the same number, then that is my common ratio. And remember our short formula for that, we can say that the first term, so 24, times that ratio of 4 raised to the I minus 1, because notice I'm already on term a sub 1, right? I'm on that first term. So I'm going to do I minus 1 up there. Then I can put that into my sigma notation. As long as I starts at 1, 1 minus 1 would be 0, 4 to the 0 is 1, times 24, I'm getting my first term. The one trick is I don't know how many terms there are. So what I do need to do is set my term here, 6294, or 91, sorry, 456, equal to my sequence now, so that I can figure out which term this is. So equal to 24 times 4 raised to the I minus 1. Well, if I divide by 24 very quickly here, which would be helpful to have my handy-dandy calculator present, 6291456 divided by 24 comes out to 262,000. Oops. Let's go ahead and show what we're doing here. Divide by 24, divide by 24. Again, is going to come out to 262,144. That is now equal to, since we just got rid of our 24s, 4 to the I minus 1. Now comes the tricky part. If you remember with an exponential function, the way to get rid of the base is to take a logarithm. So we're going to say log base 4 of 4 to the I minus 1 is equal to log base 4 of 262, 144. On the right side, log cancels the exponential base, and essentially, again, log base 4 of 4. This becomes I minus 1. And on the right side, the logarithm of 262, 144, or the log base 4 of that number, should be equal to 9. So that's a much nice, easier number to work with. And then finally, don't forget to add your 1. I minus 1 equals 9, so add 1. Technically, this is a sub 10, or we are going to find 10 terms from 1 to 10 of this sequence. And now the beauty is we can go back and use our formula. So let's grab our formula from up top. We want to find the sum of the first 10 terms. Remember, that means the first term times 1 minus the common ratio, r. So 4 raised to the number of terms, which was 10, all over 1 minus 4. And if we type very carefully again into our calculator, make sure we're very careful about those parentheses. I would put parentheses around your numerator, as well as around your denominator, although you could just say the denominator technically is negative 3. But you will come out to 83886 00, basically 8,388,600, and that will be our overall summation. So notice again, we wanted the sigma notation, which we have very nicely in green here. Okay. We were trying to find that first, and then we also have our final answer down here. So make sure you get both parts of that so you can answer the full question. Hopefully that helps you with geometric series. If you want more examples or need some help with that, again, you can always look it up in your book, look up more videos on the internet, or of course you can always stop by and ask your teacher. Good luck, happy multiplying, happy adding, and have a great day.